Hello everyone, I'm Chu Hen from AAAI of Tsinghua University. I'm very happy here to present our work. The title is Policy Search by Target Distribution Learning for Continuous Control. It is a joint work with Yuanqi Li and Jian Li. The continuous control problem is a reinforcement learning problem where the action is specified by continuous values. It has many real applications, such as robotic control, finance, and healthcare. There are two main streams to solve the RL problem: the value-based methods and the policy-based methods. However, value-based methods are not well suited to solve the continuous control problems, since it is hard to convert the learned value function into an executable continuous control policy. On the other hand, policy-based methods are suitable where the policy is learned directly. Currently, we already have many algorithms for continuous control with good asymptotic performance or sample efficiency, such as TRPO, PPO, SAC, DDPG. However, robustness is also important and especially important for real applications. In real applications, we may deploy a preliminary policy to real systems and further train the policy using real samples. In this case, an unstable training process may cause damage to real systems. Also, high variance across different runs or different hyperparameters is undesirable, since we may have to run multiple times to obtain a satisfactory performance. Therefore, the objective of our work is to find an algorithm that not only with good performance, but also being robust. In this paper, we conducted experiments to demonstrate a source of instability that exists in some policy-based algorithms. Especially, we found that such instability exists in a very simple environment for PPO. Our experiment is as follows. The cost, which is the negative reward, equals to minus a squared, where a is the action, and it is a real number. The state S is also a real number, uniformly sampled from 0 and 1. Notice that the cost does not involve the state, therefore the state contributes nothing to the environment. Obviously, the optimal policy for this environment is A equals 0, which means that the agent should output 0 action all the time. The policy in PPO receives a state and outputs an action distribution. Then we can execute the policy by sampling an action from the distribution. Here, the action distribution is a Gaussian distribution specified by mu and sigma. After some mathematics, we found that the average gradient is inverse proportional to sigma outputted by the policy. We will soon find that this leads to the instability. Let us look at the training process of PPO in this figure. The x-axis shows the training iterations. The y-axis here is the cost of the policy during the training. The lower the better. The y-axis here is the variance outputted by the policy during the training. Since the optimal policy is a deterministic policy, the variance should approach 0 during the training. We can see from the figure that at the beginning of the training in PPO, the cost and the variance of the policy quickly decreases. However, when the variance of the policy becomes smaller and smaller, the average gradient becomes larger. The large gradient results in a large update, and the large update may drive the originally near optimal policy far away from the optimal. This results in instability. We observe such instability in our experiments that we can see from the figure. On the other hand, the orange and the green lines are stable and approach the optimal policy. They correspond to two variants of our algorithm. Next, I'm going to introduce our algorithm, Target Distribution Learning, abbreviated as TDL. Our algorithm is based on a conservative policy iteration framework, and it is an ARM policy algorithm, where the policy is updated iteratively. In each iteration, we collect a number of samples following the current policy, and then we update the policy based on the collected samples. Many algorithms of this kind directly update the policy network following the policy gradient. To construct a robust algorithm for continuous control, we propose to decouple the policy gradient backward process. That is to first set the targets of the policy based on the collected samples, and then update the policy network towards these targets. Specifically, we set a target distribution separately on each sample. The target distribution on each sample tells the algorithm what action distribution the policy should output the next time when the agent faces a similar state. Since the target distribution is set separately on each sample, the objective of the target distribution setting can be more carefully designed. One successful variant of our algorithm sets the target relying on the evolutionary strategy, DES, rather than the gradient of the cumulative reward. We found that setting the target through the evolutionary strategy is equivalent to maximizing the probability that the policy is improved over the previous policy in the last iteration. That is to maximize the LT2 term for each sample indicated by T. We are to find a new action distribution. This is a Gaussian distribution specified by mu and sigma, such that the probability that we obtain a positive advantage function over the old policy is maximized. This indicates that our policy will be improved on this sample. On the contrary, many existing algorithms maximize the policy improvement in each iteration. That is to maximize the LT1 term. We found that our objective, the LT2 term, results in a more robust performance. Following the ES algorithm, we can obtain one variant of our algorithm, which we call TDLES. Notice that for each sample, the previous policy first outputs an old action distribution, which we show by the blue dashed oval. Then we sample an action from this distribution and returns to the environment. That is the red dot here. After we finish the rollout, we can estimate the advantage function on this action sample based on the reward from the environment. The advantage indicates the goodness of the action sample over old action distribution. Based on all this information, we can propose a better action distribution in the next time when we face a similar state, which we call the target distribution, indicated by the green ovals here. In TDLES, we proposed a target distribution for each sample indicated by T. When the advantage estimate on this sample is positive, this means that this action sample may indicate a good direction for exploration. Therefore, the next time when we face a similar state, we hope the action distribution could be closer to the action AT that we sampled in this round. Therefore, we set the target distribution to be a step forward towards AT. Notice that we use a nu to control the step size. On the other hand, if the advantage estimate is negative, say the action sample is worse than the old action distribution, instead of pushing the action distribution to the opposite direction, we remain the action distribution the same as the old one. We found that this contributes to the robustness. Since a bad action sample does not necessarily indicate the correctness of the opposite direction, This is especially true when the dimension of the action space is high. It is safer to stay where we are previously if no more information is provided about a good direction. By the way, it is quite flexible for us to design rules for the target setting, as long as the targets lead us to a locally optimal policy. Therefore, we can incorporate some prior knowledge for robotic control to the design of the target setting. And this results in a revised version of TDLES, which we call TDLESR. The prior knowledge is that in robotic control, the state representation does not change too fast, so we can set the targets based on the adjacent state samples in the trajectory. Next, we are going to present 4 sets of our experiment. The first set of our experiment is on the standard benchmark test from Wujuko. Here in our slide, we only put 3 of the tasks. The lines in the figure are the training curves of the algorithms, and the stars indicate some more basic versions or ablated versions of our algorithm. The result shows that TDL achieves a comparable asymptotic performance and sample efficiency to some state-of-the-art algorithms. But most importantly, TDL is quite robust during the training. The numbers in the parentheses indicate the variance of the training curve. We can see that the numbers of TDL algorithms are smaller than the previous algorithms. Here is our second set of experiments. Recall that we decoupled the policy gradient backward process. We first proposed the targets in step 2, then update the policy network in step 3. The advantage is that once we propose and fix the targets in step 2, the hyperparameters in step 3 will not largely influence the final performance. In policy algorithms, once we collect a batch of samples, we want to make full use of them. Naturally, we hope to train the network for more epochs based on these samples. However, if we do not have fixed target, more training epochs will drive the network away. We have fixed targets for the policy network training, therefore we do not suffer from the problem. This advantage is demonstrated in our experiment. When we increase the training epochs in each iteration from the blue to the red, the performance of PPO degenerates significantly. However, our algorithms are not significantly influenced. Recall that we are following a conservative policy iteration framework. Constraining the KL divergence between the new and old policies in each iteration is the key to ensure policy improvement for each iteration. Unlike previous methods, our hyperparameters have a direct connection with the KL divergence between the new and old policies, and therefore we have more basis to choose the appropriate hyperparameter rather than sweeping over all possible parameters. Our experiment also demonstrates that TDL can achieve a similar performance while being more conservative in terms of policy update. Look at the blue, orange, and red lines in the figure. They indicate a low KL divergence between the new and old policies in each iteration, compared with other algorithms that are based on conservative policy iteration. Finally, we did experiment on hyperparameter sensitivity analysis and demonstrated that our algorithm is robust to different hyperparameter settings. In conclusion, we proposed our target distribution learning (TDL) policy iteration algorithm that decouples the policy gradient process for robust continuous control. Our algorithm achieves state-of-the-art performance on Wujuko tasks. Most importantly, it is robust during the training and across different rounds with different venom seeds. It is robust to the number of optimization epochs, and therefore can safely increase the sample reuse for the maximum sample efficiency. Our experiments show that TDL updates more conservatively while being sample efficient. Also, our algorithm is robust across different hyperparameter settings. Okay, this is the oral presentation of our work. You can contact me at from this email address. You can also download a source code from this link and also a full paper with supplementary materials from this QR code. Thank you for watching this video.